Hey guys, so here chapter 8. So covalent bond number. So you have a single, double, triple bond. So for example here, a carbon, single bond carbon, the length is 147 picometers. In a double bond, yes, carbon double carbon bond, the length is 134 picometers. In a triple bond, C triple C, the length is 120 picometers. What's happening here? When the number of bonds increases, the length is get shorter, right? And when the length is decreasing, the strength increases. That means triple bond is stronger than double bond, and double bond is stronger than a single bond, okay? So next topic is about resonance. Resonance represents an overall delocalization of electrons in a molecule. So it's when one little structure cannot fully describe the bonding. It's like this, the ozone, double bond can be this one on the right or can be on the left, can be this one on the left or this one on the right. So these electrons here keep moving, right? Okay. So, and then you have ways to find which one is the dominant structure. So you have assigning formal charge. Formal charge is the charge an atom would have if all the electrons in a covalent bond were shared equally. So how can you calculate formal charge? Is valence electrons minus lone electrons minus bonding electrons. And after we calculate the formal charge, the dominant structure will be the one in which atoms have formal charge closest to 0. And if it is not, another way also, like it's putting a negative formal charge on the most electronegative atom. Okay. So for example, we have these two structures here, C double O and C triple O and C single O. Which one is the correct? Carbon dioxide with two double bonds or carbon dioxide with a triple and single bonds here. So let's calculate the formal charge. So the formal charge for this carbon here, like little structure 1, the valence electron for carbon is always 4. Group 4A, so 4 valence electrons. Here, for A, 4 valence electrons, carbons. Minus lone electrons. How many lone electrons do we have here around the carbon? 0? So, okay, so 0 valence electrons. Minus numbers of bonds. How many bonds do we have around this carbon? 1, 2, 3, 4. So minus 4 here. So this carbon formal charge is 0. That is great. That means probably this one is the correct structure. But then you still need to check oxygen, right? So we have two oxygens here. In that case, the two oxygens are exactly the same way. Like both have 4 lone electrons and 2 bonds. So let's calculate it here. Oxygen, valence electrons is always 6, minus how many lone electrons? 1, 2, 3, 4. So each oxygen here, right? So this formal charge here will be for both because they are equally. So minus 4 lone electrons minus 2 bonds. Okay, so the formal charge for both oxygen here is 0. Right? And you saw the carbon is also 0. And why the C triple O single O is not correct? Because if you calculate the formal charge here, oxygen will not be 0. Carbon, yes, will still be 0, the formal charge, but for example, for this carbon here, for this oxygen here, how many valence electron? 6, right? How many lone electrons? So 6 dots, so 6 lone electrons, and minus how many bonds? Here, 1 bond. When you do the math here, will be -1, the formal charge. And the same thing for B, for this oxygen here that I called B. When you do the math, here will be +1. That means this one is not the correct structure because the structure A got the numbers, the formal charge closest to 0, then the second one here. Okay, for example, between these three structures, which one is the dominant one? Okay, let's check. Let's check. The first one, we have just 1, 0, +1, and -2. So already know this one will not be structure, the dominant structure, right? But between these two structures, which one will be the dominant one? This one with -1 in nitrogen, or this one with -1 the sulfur? So you have 2 zeros and -1. Which one gonna be the correct one? The correct one will be the one that the negative formal charge will be in the most electronegative atom. So -1 in sulfur, and -1 in nitrogen, -1 in the sulfur. Sulfur is right here, nitrogen is here. So the electronegativity increases from left to right and from bottom to top. The nitrogen, and you can check out the electronegativity value. The nitrogen has higher electronegativity than sulfur. That's why this one, the dominant structure, dominant lead structure. Okay. So type of covalent bonds the bonds can be polar covalent bonds or non-polar covalent bonds. The non-polar is when two atoms share electrons equally, and the polar covalent bond is when two atoms share electrons unequally. How can you verify, how can you check if they are polar or non-polar? You can find out by calculating the electronegativity difference. You have a table, right? Electronegativity table, each element has a number, and the number here is the electronegativity value. So if the difference between two atoms is below 0.4, that means the bond is a pure covalent, or also called non-polar covalent. But if the electronegativity difference between two atoms is between 0.4 and 1.8, you have a polar covalent bond. And if the electronegativity difference between two atoms is above 1.8, that means you have ionic bond. So, for example, here, this question 1. In each case, which bond is more polar? Boron chlorine or carbon chlorine? Let's check here. Boron chlorine. The boron electronegativity is 2, and chlorine is 3. When you do the difference here will be 1. Okay, use the absolute value, like 3 minus 2, 1. And the electronegativity difference between carbon and chlorine is, so carbon electronegativity value is 2.5, chlorine is a -3. You check all values here. When you do subtraction, 3 minus 2.5, you have the difference is 0.5. That means which one is more polar? Boron chlorine or carbon chlorine? The answer will be the one that it has higher electronegativity differences. So the answer is gonna be boron chlorine. And the last topic in chapter 8 is about exceptions to the octet rule. So we saw previously, right, the electrons are sharing or exchange electrons to achieve 8 valence electrons, right, usually. Like the hydrogen will be happy with only 2, but or another one mostly will be stable with octet rule. But we still have exceptions. For example, here, in this bond here, nitrogen monoxide, you have ions or molecules with odd numbers of electrons. So here they are. They do not have the octet rule. In ions or molecule with less than octet, the elements in the second period before carbon can make stable compounds with fewer than 8 electrons, like boron. So boron here, right, is in the period, second period here, and before carbon. So boron is an example of an element in the second period before the carbon that it can make stable compounds with fewer than 8 electrons, like boron trifluoride here. To give a boron a field octet places a negative charge on the boron and a positive charge on fluorine. There is not to be an accurate picture. So if you check this one here, the BF3 with all single bonds is a dominant structure. And it's gonna be more stable than this one, these ones here. Ions or ions or molecule with more than 80 valence electrons, we call expanded octet. Like phosphorus can have, like, for example, here, 10 valence electrons right here. So when an element in period 3 or 6 can use the orbitals to make more than 4 bonds and be, like, for example, here, phosphorus make 5 bonds. Also, one exception too. So the exception is can be have less than 8 electrons or more than 8 valence electrons. Okay, so it's the end of chapter 8 here.